Hello and welcome to The Conversation Weekly.
This week, we speak with two astronomers who have spent decades working on the James Webb Space Telescope. Set to launch in late December 2021, the telescope is poised to answer some questions about the beginning of the universe and to help astronomers learn more about planets around other stars.
The key goal of the James Webb Space Telescope is to probe the very earliest time in the universe.
The telescope is enormous for something that gets launched into space.
And I talked to a researcher who's been examining what tactics the food industry are using to boost sales of ultra-processed foods in middle-income countries like Brazil and South Africa.
By 2025, the sales of ultra-processed foods in middle-income countries will reach equivalence with high-income countries.
I'm Gemma Ware in London.
And I'm Dan Marino in San Francisco. You're listening to The Conversation Weekly, the world explained by experts. At the north edge of South America lies French Guiana, an overseas region of France. And on the outskirts of its port city of Kourou, there is a rocket launch pad, the European Spaceport.
Later this month, if everything goes to plan, this is where the James Webb Space Telescope will launch into space on an Ariane 5 rocket.
Astronomers have been waiting for this moment for literal decades. After years of delays and a few technical setbacks, including one in late November, the James Webb Space Telescope is scheduled to launch on December 22nd. I've been talking to two astronomers about the telescope to find out why it's different and so special compared to what's gone to space before, and what they hope to see with this incredible new tool. Martin, first of all, thank you so much for being willing to speak with us this week. If you could just introduce yourself, give me your full name, where you work, what you do.
So I'm Professor Martin Barstow. I'm an astrophysicist and space scientist at the University of Leicester in the UK. I also chair the council at the Space Telescope Science Institute, and that's my personal involvement in James Webb Space Telescope because the institute will be the operations centre after launch.
So tell the listeners, what is a space telescope really, and why do we want to send a telescope to space?
Well, the title Space Telescope is really the sort of job description. It's a telescope to study the universe, and it's in space, can be orbiting the Earth like the Hubble Space Telescope, or it can be more distant. Why do we want to go to this trouble is an important question, because we can do a lot of astronomy from the ground, but there is this bit of a problem called the atmosphere. It keeps us alive, but it actually gets in the way. And particularly in certain parts of the electromagnetic spectrum, the atmosphere blocks quite a lot of light from some wavelengths, particularly in the infrared, which is where the James Webb Space Telescope will operate. Also, the atmosphere is warm. The atmosphere gives you a lot of background radiation, which can swamp what it is you're trying to observe. So we need, in the case of the James Webb Space Telescope, to take it well away from the Earth, outside the atmosphere, to get away from the blocking effect of the atmosphere, but also to take it somewhere where we can keep it really cool so that we can detect the very faint signals that come from the distant universe.
I want to just ask you a little bit about the history of space telescopes and the forefathers of James Webb. So when was the first space telescope launched into orbit?
It depends how you define telescope. If you think of something like a conventional telescope that has the same kind of optics as we're familiar with these days, then one of the very earliest was a telescope called Copernicus, which was launched in the very early 1970s, which had an ultraviolet telescope on board. It was designed to look at that part of the spectrum which can't penetrate the atmosphere. But the ideas for a space telescope, a little bit like Hubble, came first in the mid-1960s. And an astronomer called Lyman Spitzer was one of the earliest people to suggest that getting into space with a telescope would be a really good thing to do. And in fact, his ideas were what eventually turned into the Hubble Space Telescope.
Let's talk Hubble. It's Hubble, right?
Absolutely, yeah. I've been working on Hubble pretty much since it was launched, so it's been part of my entire career.
And how important has Hubble been to the goal of astronomy, to the science of looking into the universe?
Hubble has probably been one of the most important telescopes ever built. Hubble, being outside the atmosphere, has a tremendous advantage. The sky is incredibly dark for Hubble compared to working from the ground. And so it's been able to study a huge range of different areas of astrophysics, particularly with its very wide wavelength coverage. It covers ultraviolet light, visible light, as well as infrared.
And when was Hubble actually launched into orbit?
Hubble was launched in 1990, and of its first year or so, it was problematic because they found that it didn't focus correctly, and that was a serious disaster for NASA and a big challenge for astronomers to use it in that condition, but also eventually for NASA and its astronauts to go and fix the problem, which they did very successfully.
So if you just had to give us a highlight reel here, Martin, what are some of the biggest discoveries made by Hubble, aside from certainly the incredible photos we've gotten back on Earth?
Yeah, the photos are amazing, but underneath all those photos is a lot of data that isn't so visually beautiful, but nevertheless very important. Hubble was actually put up in space to measure the size and age of the universe, and it did just that. But what we found wasn't actually quite what we expected. The idea was that we calibrate the distance scale, measure the expansion of the universe, and measure its age. But what was actually discovered was that the universe's expansion is accelerating, which was an enormous surprise. At the other end of the spectrum of scale is the work that Hubble has been doing on extrasolar planets. Those are planets orbiting other stars. And when Hubble was designed and when it was launched, nobody had any idea that it would be able to observe objects like that. In fact, none of these planets had actually been discovered at that stage.
Hubble launched in 1990, and it's still going super strong today. But even before Hubble got into orbit, astronomers had already begun designing the next space telescope, this one named after James Webb. James Webb ran NASA for most of the 1960s, which was a huge decade for the American space program. He saw the Apollo missions to the moon, but also was a huge proponent of the scientific capability of NASA. He gave a lot of support to the US Space Agency's science program and argued that they should try and get a large telescope into space. The James Webb Space Telescope has been a $10 billion, 25-year project. The actual design work began in the mid-1990s, and the telescope was set originally to launch in 2007. That was delayed until 2018, and then a second issue during its testing period pushed back launch again. The pandemic was the last speed bump, but the telescope is finally set to launch this month, December, in 2021. What is James Webb's mission?
A key goal of the James Webb Space Telescope is to probe the very earliest times in the universe, to look back to find the earliest stars that are forming at the very beginning of the universe soon after the Big Bang, and looking at how those stars are collected into galaxies and how these galaxies are formed. We don't know that, and Hubble, because it doesn't work in the right wavelength range, can't do that for us. It doesn't have a big enough mirror. It doesn't cover the right part of the spectrum. So James Webb is an infrared observatory, and it's got a very large mirror. Its mirror diameter is 6.5 meters, more than twice the size of Hubble. So it's specifically focused on doing that particular job. But it can observe other things. And another important task is to study extrasolar planets. These are easier to see and study in the infrared than they are in the visible, because they're less swamped by the parent star.
And the James Webb Space Telescope is headed out to a place called a Lagrange point. So where is this Lagrange point? What is a Lagrange point? And why is the telescope headed there?
So the L2 point is a point some distance from the Earth, about 1 million miles away, on the opposite side of the Earth to the Sun. And the way gravity works is that the alignment between the Earth and the Sun makes this point not a pure orbit around the Earth, but a stable point where a spacecraft can exist. And essentially, it's in orbit around the Sun, not around the Earth. It follows the Earth around in its orbit. And so it keeps the Earth between it and the Sun. So it's a great place to put a telescope, because you are shielded to an extent from the Sun itself, which can heat the telescope up. You're a long way from the Earth, which can also heat the telescope up. And you're a long way from other interferences like other satellites, and radio waves, radio signals. So it's generally a nice quiet place and essentially what we call low background.
Just to kind of put it in simple terms, it's almost the difference of going to a high, cold, crisp desert and looking up at the stars, or doing it in the middle of a city. Is that more or less?
Yeah, that's a good analogy, actually.
Different teams of scientists have been involved in developing and designing different instruments on the telescope itself, and I called up one of them who's based in the US. So, Marsha, first of all, thank you so much for being willing to speak with us for the podcast, and glad to have you on the show.
Thank you very much, and I'm happy to be here and getting excited for the launch.
So, can you introduce yourself, please? Tell the listeners who you are, what you study.
Okay, I'm Marcia Rieke. I'm a professor of astronomy at the University of Arizona, and I'm also the principal investigator for the near-infrared camera, NIRCam, on the James Webb Space Telescope. And I'm very excited to be part of that mission because my research has always involved studying galaxies and how they change and evolve over time. And that mission is just super well designed to do that.
So, Marsha, what are you going to be doing day of launch? Are you going to be sitting nervously with some popcorn or doing some science? What's your role that day?
Well, since the launch is at 5:20 a.m. here in Tucson, what we're going to do is we're going to take our large lecture hall. We'll live stream the launch. We'll have some coffee and pastries, and my team and many of the people from the observatory will watch it all together.
Awesome. And you must be very excited, right?
Oh, yeah. Yeah, because the sooner we can get this into space, the sooner I can start having some fun.
Paint me a picture with your words, if you will, Marsha. Tell me what the telescope is like. How big is it?
Oh, the telescope is enormous for something that gets launched into space. The primary mirror is over 21 feet across. It's comprised of 18 segments, all of which have to be aligned, and they're all gold-coated, so it's very pretty to look at. And then there's also a compartment containing the instruments that's bigger than a phone booth, and then underneath there is a large sun shield about the size of a tennis court that keeps the telescope and instruments cold so they work well in the infrared.
For those that don't know, Marsha, can you explain what infrared light is?
The word literally means beyond red, and so it's the part of the light spectrum or electromagnetic spectrum that has longer wavelengths than red light. Sometimes it's called heat radiation because if you imagined looking at a burner on your electric stove and turned it on just a little on low, you wouldn't see the burner looking different, but if you held your hand a little ways above it, your hand could still get warm, and that's infrared.
Got it. So why infrared? Why do we want to look for infrared light here?
Well, there are several reasons. One big reason is that we know that the expansion of the universe causes things to appear to be moving away from us. The universe is literally getting bigger all the time. And one way to think of it, the classical analogy is if you think of a loaf of bread dough with raisins and you leave the bread dough out to rise, the raisins get further and further apart. And that's similar to what happens with the universe, that it's expanding like the bread dough is expanding, and the galaxies are the raisins getting further and further apart. And this expansion happens in such a way that the further away a galaxy is from us, the faster it appears to be moving away. And this effect was discovered in the 1920s. So it's well understood at this point. And that motion causes something called the Doppler shift that shifts light redward. And so if we want to study the most distant galaxies, we have to look in the infrared because the light gets shifted beyond the normal red part of the spectrum.
Okay, so the telescope is designed to deal with infrared light. But can you explain the physical technicality of how this all actually works?
Okay, how this all works. Light from the sky comes into the mouth of the telescope, hits the primary mirror, bounces off there. It goes out to a little mirror called the secondary mirror because it's smaller. which then directs it down through an opening in the center of the primary mirror, and the instruments are mounted on the back side, and so the light then hits some other mirrors that can direct it to the instruments and keep the guiding going very nicely. And so there are 4 instruments that analyze this light that comes in different ways.
What are those 4 instruments?
There's a near-infrared camera called NIRCam, a near-infrared spectrometer called NIRSpec, and the difference between camera and spectrometer is that the spectrometer subdivides the light so that we can learn more about what the source is made of and so on. Then there's a mid-infrared instrument called MIRI that has both cameras and spectrometers. And then there's a 4th instrument provided by the Canadian Space Agency that is called NIRIS, Near-Infrared Slitless Spectrometer, that's optimized for exoplanet studies.
There is a ton of different science that's going to come from these 4 instruments, but a particular research interest of Marcia's is the history of the universe and the process of how galaxies form. The James Webb Space Telescope is going to help astronomers answer these questions by looking back through time itself. How can you look back in time with a telescope? Because that seems a little wild to those who aren't familiar with the way this stuff works.
What we do is we take advantage of the fact that light doesn't travel infinitely fast. We think of it as going infinitely fast, but actually it has a 186,000 miles per second limit. That means that if we know how far away something is, then we know how long it's taken the light to come here. We can calculate it. And we can measure the distances by measuring how much the light is shifted to the red. So that's an unusual form of distance measurement, but that's how we can tell how far away these distant galaxies are. So, for example, we know that the Big Bang happened 13.8 billion years ago. If we observe an object and discover that it's at a distance where it took light 13.4 billion years to come here, we difference those 2 numbers, and voila, we're seeing that galaxy as it was at an age of 400 million years because it took so long for the light to come here.
So galaxy formation is something that you've been interested for a lot of your career, and one of the things astronomers like you are looking for is called first light. What does that mean?
Literally, first light would be when the very first star in the universe collapses enough to start making light as the sun does, but a single star that at that distance can't be detected. So there'll be a cloud of gas that's being pulled together under the influence of gravity, and it will fragment into individual stars. And once enough of those stars get fully formed and making light, then we'll be able to see that as one of the first galaxies or first big star clusters. And at least in the context of Webb, that's what we mean by first light.
And what is the mystery around first star clusters right now? What don't we know?
Well, we don't know what their size is. And we have some clues that there are a range of sizes of galaxies or star clusters that are formed early on, but we don't understand what that range of size is, and nor do we understand very well how those pieces will come together to form bigger and bigger galaxies. We see some evidence of that, but we don't really know what happens in the first few stages.
So we've got Big Bang and we've got later galaxies. And is there just kind of a black box, if you will, in between there?
Yeah, in fact, some people have called that the Dark Ages because there is a period before the first stars form and when we can finally start detecting groups of galaxies. And so there is a period that we just don't know anything about right now.
So why is James Webb so good at looking at these things?
2 key things are that it's big and it's cold. So that helps the sensitivity. And then the light sensors inside the cameras and spectrometers are exquisite. They are the best we have ever made. And for example, with my instrument NIRCam, we'll take images through filters that select a series of wavelengths. And by looking at the distribution of brightnesses across that suite of filters, we'll be able to estimate the distance to the galaxies. That'll give us a list of ones we think are very far away. Then we can use near spec, which can measure the redshift very accurately. Will tell us which ones are exactly how far away, and then we'll have our list of first light galaxies.
Once the fun begins, what's the first thing you guys are going to do? Walk me through the kind of scientific process here, if you will.
The very first thing that we're going to use NIRCam for is not scientific per se. It's to help get the 18 segments of the primary mirror lined up so they act like a single smooth mirror. That's the first job. And that starts happening about 30, 35 days after launch when we've cooled off enough to start operating. In the 4 to 6 months after launch, we'll be working on testing all of the different ways one can observe using the instruments. And then roughly 6 months after launch, the mission will go into routine science operation, and it will start working on a timeline that's been laid out by people at Space Telescope Science Institute, where astronomers have already proposed to use Webb, and they've assembled things into an efficient order to observe.
So what happens? You take the telescope and you point it at a chunk of sky that has been predetermined, and then what comes into the telescope?
It's basically delivering digital images that when you get it, it just shows up on your computer screen like a picture from your digital camera.
What are some of the things people like yourself are most excited to do with these images once you find some of these first galaxies?
I want to go through and find out how many of each mass gets formed in the very first stages, because that may settle some arguments about how galaxy formation proceeds.
What are some of those arguments?
Well, I'm not a theoretician, so I don't back any particular model. I'll compare it against different people's. But exactly how dark matter works in shaping these first steps in galaxy formation is not very well known.
Dark matter, that's the undetectable stuff for humans, but we can see its effect via gravity. So what else can we learn?
It may even be the case that if we understand the numbers of sizes of galaxies in the first steps, we'll get some insight into how the dark matter works. We think dark matter comes in clumps of, we call them halos, different sized blobs, and that's what controls how the galaxies come together. But we really need to prove that in more detail than we've been able to do so far.
Just in general, Marcia, what are you most excited about when it comes to James Webb?
I'm torn between finding the most distant galaxy and finding an exoplanet whose atmosphere has a composition similar to Earth's.
Remember, exoplanets are any planet orbiting a star that isn't our sun. There are a ton of missions hunting for exoplanets, and almost every day, another planet is found orbiting a distant star. But current telescopes are really just not able to understand what these exoplanets are made of, nor what their atmospheres are composed of. And as Martin Barstow explained, that's where the James Webb Space Telescope will come in.
So James Webb is there to do something that we call characterization. And what we mean by that is that basically see what the planets look like. And by doing spectroscopy on these planets, either by shielding the telescope from the light of the nearby star, a technique called coronography, so that you can observe the planet just on its own, or by doing what we call transit spectroscopy, where you watch the planet pass across the face of the star and you examine the difference between the in and out of transit light. By using those techniques, you can actually measure things like atmospheric composition and the temperature, which you can't do any other way. And if we can do that, we may then be able to infer the structure of the atmosphere from the data that we have. We might even be able to see evidence for the existence of structures in the atmosphere, such as clouds.
You're talking about temperature, structure of the atmosphere, clouds. That's some pretty fine-scale data to get on something literally hundreds to thousands of light years away. I mean, this is some incredible science, though, right?
Yeah, I definitely agree that it's incredible science. Every time we build a new facility like James Webb, we're pushing the frontiers of science further and further. I don't think we'll ever get to the end of that journey, to be honest, But I think it's an important part of what we're about as human beings, is wanting to know, wanting to learn about our origins. How did we come to be? And understanding how the universe came into existence and then how it developed is part of a long journey to the existence of life. And I think it's probably a bit speculative that we might find evidence for life using this particular telescope. It's not really optimized for that. But the next generation of telescopes...
The next generation of telescopes might have more of a chance. In early November, the National Academies of Sciences, Engineering, and Medicine published its decadal survey called Astro 2020, a review of what kind of astronomy equipment the US and the world should be investing in over the next 10 years.
In fact, the outcome of the decadal survey that was just conducted and published a few weeks ago is suggesting we build another very large UV and optical and infrared telescope, a little bit like Hubble, but much, much bigger, to actually carry out that next step of the journey, which is to search for evidence of planets that look like the Earth and which may be hosting life. And to do that, we have to find planets that look a bit like the Earth. Then we have to find planets that are in the right zone, the so-called habitable zone, the distance from their sun. And then we need to characterize those planets, to study the atmosphere and to look to see what the components of the atmosphere are so that we can infer if there are biological processes going on. To do that, we need a big telescope that can observe across the UV, optical and infrared. And we also need some very sophisticated techniques like coronagraphy to block out the light of the parent star so that we can focus on the light from the planet, which is going to be very, very faint, even for nearby stars in a relatively local part of our galaxy.
Martin's actually involved as an external observer on one of the proposals for this kind of telescope, called, in this case, the LUVOIR project, an acronym for the Large Ultraviolet Optical Infrared Surveyor. Martin, in the meantime, is also the chair of the Council of the Space Telescope Institute. This is an international body that governs the James Webb Space Telescope once it's up and running, deciding who gets to do what and when and how. So this kind of data that you're going to be collecting, whether it's on exoplanets or into the deep space and deep history of the universe, there must be a long list of astronomers that are hoping to, please point James Webb over there, give us that, give us this.
Absolutely.
How do you guys deal with that, and what's that process like?
So the process is pretty straightforward. It's a competition. So some of the people who built James Webb and built instruments on James Webb get a fraction of the time early in the mission, which is called guaranteed time, which is essentially a payback for the enormous effort over several decades they've put into actually making James Webb a facility that everybody can use. But then the rest of the time, and as James Webb continues, more and more of the time is an open competition. And that means that groups of astronomers write proposals for what they want to observe. Those proposals are reviewed by panels of astronomers, and then what are deemed to be the best ones are selected. And that's a hugely competitive process. 10 times more time is requested than is actually available. But it's very democratic, and it's very open and transparent.
And 30 plus years on from Hubble's launch, is Hubble still booked out for the next years?
Oh, yeah. I mean, it's still a factor 10 after 30 years. And like many astronomers, I put in my proposal for Hubble because that's an instrument I've used many times. And I didn't get any time this time around. And I was disappointed, but that is the game.
What are you most looking forward to once James Webb starts pointing its lens and its mirror and its sensors out to the stars?
To be honest, I'm just interested in seeing any image. The most important thing for me is to see the telescope working. In a way, like everybody, we're so nervous as well as excited about this process. And we know, those of us who are close to it, know what can go wrong, that it's a complicated instrument. It's been very well tested, but there are no 100% guarantees in space research. And we cannot go and repair this one. It's too far away. So everything has to be perfect. So I don't care what the first image is. I just want to see an image that's in focus.
Martin, I want to thank you so much for taking the time to talk with me today.
Thank you. It's been a great pleasure for me as well.
Stay tuned to the conversation for more analysis about the James Webb Space Telescope in the coming weeks and months as we hopefully start to get some cool images back from the deep, deep reaches of space.
Now, we're moving on to another story altogether. This one far more down to earth and closer to our kitchens. It's about food, in particular ultra-processed foods such as soft drinks, cakes, snacks, or frozen meals.
Oh, so delicious, but not the best for us, right, Gemma?
Yeah, exactly. But these kind of ultra-processed foods are big business for the companies that make them. And in recent years, they've realised that the fastest growing markets for these kind of snacks are in middle-income countries such as South Africa, Indonesia, China, and Brazil. To find out more, I called up a researcher who's recently published a study on the tactics some of these companies are using to target consumers in these countries.
My name's Edwin Kwong, and I'm a research fellow at the School of Population and Global Health at Melbourne University in Australia. And part of my research involves looking at the commercial determinants of health and also specifically ultra-processed foods. It might be a term that people aren't particularly familiar with, but essentially ultra-processed foods, they're products created by a series of industrial techniques and processes. This can include things like breaking down whole foods into separate components like sugar, oils and fats, proteins and fibers. And then they're subjected to sort of more modifications with chemical and industrial techniques. And then to add to that, more additives like flavor enhancers, colors, artificial sweeteners, they're quite commonplace in ultra-processed foods as well. So all of this put together means that they're deliberately designed to be particularly attractive to taste, smell, or see.
Okay, so what kind of foods? Give us some examples if you're going down your supermarket aisle.
So these can include things like carbonated soft drinks, sweet and salty snacks, like potato chips and that sort of thing, any kind of candy, energy drinks, instant soups, noodles, and even baby formula. So you can see that they comprise a massive range of these common products.
And I guess many people are aware that these kind of foods aren't perhaps the healthiest choice when they're coming to choose a meal. But what risks do scientists like you know that they actually have for the people who eat them?
So they're designed to be, more addictive. Essentially, they trigger our on switch in our brain to make these foods more pleasurable to eat and motivate us to keep on eating. But at the same time, they inhibit our off switch to make it more difficult for us to stop eating and to sort of turn off that off switch in our brain that tells us we're full. So both of these things combined together means that it's really hard to stop eating these really tasty foods. And they're harmful to health for two reasons. Firstly, because they're often quite high in calories and added sugars, in sodium and trans fats, which we all know to be harmful to us when consumed in excess. But also, ultra-processed foods are harmful to health because of how they're produced. So all of these extra artificial additives that they contain, they make it very harmful to health. So the consumption of ultra-processed foods is then associated with a host of non-communicable diseases like type 2 diabetes, hypertension, and other vascular diseases, so some cancers, and also higher rates of obesity as well.
So where in the world are people eating the most ultra-processed foods?
Yeah, so at the moment, it is still people in high-income countries largely that consume the most ultra-processed foods. So, for example, in the United States, 58% of dietary energy intake came from ultra-processed foods in 2009 to 2010, and that's likely to have gone up since. In our research, we discovered that by 2025, the sales of ultra-processed foods in middle-income countries combined will reach equivalence with high-income countries. And for ultra-processed beverages, they're already higher in terms of sales volume in these middle-income countries than high-income countries. And importantly, in terms of the growth and the trend of sales of ultra-processed foods and beverages, they're much higher in lower and upper middle-income countries compared to high-income countries, where the markets are actually shrinking. Of these countries like Indonesia, India, China, Brazil, and many sub-Saharan African countries like Nigeria and South Africa, this is where most of the world's population lives. So this is a major risk to people living there. And of course, they're important drivers of economic growth globally over the next couple of decades. It's perhaps pretty natural that these companies are then focusing on expanding the operations there.
Okay. So let's get into talking about the new research paper that you and some of your colleagues have published. So you've been looking at the strategies that the companies behind these ultra-processed foods are using to promote their growth in industrializing countries. It breaks it down into two main types of strategies, the business side of things and then the political side of things. Can we start by talking about the business side? So what are the kinds of techniques that these companies that you're looking at have been using to increase their market share in these industrializing countries?
So these companies, what they do is they invest heavily in foreign countries, so countries that their headquarters are not based in things like factories and distribution centers, but also in acquiring some of their domestic competitors. And this last strategy is really particularly successful because these transnational corporations, they don't just acquire the tangible assets of their domestic competitors, like factories and manufacturing plants and so forth, but also these intangible assets. So the existing relationships that these companies had with the local populations, an understanding of the local market conditions and preferences, and all of these really useful things when you're trying to have a market foothold in that country.
So they basically buy an existing brand and then they're able to grow that brand with the power that they have from an international perspective.
Yeah, absolutely. So with that international power and financial and political backing and the skill set that they have, combined with the local know-how, this makes it really successful for companies to grow throughout the world. So some examples are when Nestle acquired a local Chinese confectionery company, Xu Fuji, in 2011. And similarly for Coca-Cola, when they acquired the soft drinks brand of the Indian giant Parley products in 93. And this actually made it the market leader in India just with this one acquisition.
So that's the first kind of thing. What about the second strategy?
So the second one is with these large transnational corporations, they establish what we call hyperlocal distribution networks. And so what hyperlocal means is that the marketing is very focused on a target audience in a specific area. And so they're able to then reach out to people who previously weren't exposed to their products. So this can include poorer populations and rural populations. And throughout many of these middle-income countries that we looked at, we're seeing a growth in supermarkets and convenience stores, which previously perhaps didn't exist in these areas. And so they can act as, really major distribution channels for these ultra-processed foods. And one reason being that they're just cheaper than traditional foods, just purely because of the economies of scale. But also, a lot of these large transnational corporations can actually reach out to small business owners to establish partnerships directly. So one example we gave in our publication is in Mexico with the local tiendas, which are informal vendors and family-run general stores. They have established direct business partnerships with these local stores. Or, as in the case of Brazil, they can directly hire local community members to sell their products. So there's a program in Brazil that Nestle established called Nestle Até Você, which means Nestle comes to you. And they hire over 7,000 door-to-door salesmen, mainly from poorer neighborhoods. And according to their own projections back in 2010, they would visit 3.2 million households in 2010 alone.
Wow. So they've really kind of tapping into markets that hadn't been targeted before by investing in these local networks. Okay, so we've got increasing local production and buying kind of factories, etc. We've got the distribution networks. What's the third kind of business technique they're using?
Yeah, the third one is more of a general marketing promotion strategies and at the forefront of using very sophisticated and integrated marketing techniques to increase their exposure and also then, of course, the consumption of their products around the world. Two main strategies are digital marketing and also corporate social responsibility initiatives and programs. So they utilize things such as collecting behavioral data through our online experiences to then create more personalized advertising for each of us. So in terms of corporate social responsibility initiatives and programs, they're designed and intended to create greater sort of likability and acceptability of these corporations, which then in turn raises their profitability. And they can also be in a position to better loosen or resist regulations because they have what we call sort of greater social and reputational resources. So they can better, influence governments and influence the population in sort of saying that, oh, we're on your side and we're part of the solution, for example.
Okay, so that takes us kind of on to the next point, I guess. So we've talked really there about all the business side of things, but there is also a political element to their growth in these markets.
Yeah, so for many of these large companies and corporations, in order to make the business and legal and regulatory environments more favorable to them and their operations, they have to use a range of political strategies to help sustain, protect, and expand the markets. And they do this by preventing or delaying or weakening regulations. And of course, the larger these companies grow, the more concentrated and potent their economic and political power. So we saw this really clearly in Colombia when a bill was being debated to introduce a tax on sugary drinks in 2016. This had widespread societal support, but over 90 lobbyists from industry worked to influence different legislators in the Colombian Congress. And in the end, the sugary drinks tax was not passed, despite the support.
So these kind of companies, these corporations that sell food, they're not unique in their use of lobbying, but what you're saying is that they're doing it in these markets in a particularly aggressive way.
Yeah, absolutely. In countries like Thailand and South Africa, legislations were originally proposed where government would have, oversight and control of what can be advertised to children in terms of these unhealthy foods. But through lobbying, these large corporations managed to make them into self-regulatory codes, so they weren't monitored. And in the end, they weren't successful. There's been studies done to show that the amount of advertising that children saw before and after these self-regulatory codes were introduced either stayed the same or actually increased.
Following on from that then, what bits of advice do you and your colleagues have for how to rein in the marketing practices of these companies?
I'd be remiss not to say that governments have to really step up. Absolutely more needs to be done to monitor and control the consumption of ultra-processed foods. More transparency and greater transparency in terms of political donations, lobbying, and funding of research that's also required. During our current pandemic with COVID, government budgets are increasingly stretched. So we can see a bigger gap will be open for corporations to kind of step in and further entrench themselves in the fabrics of the society through acts like donating food, medical equipment, PPEs, and so forth. So, yeah, despite all these, ostensibly charitable acts, it's really important to recognize that the kind of raison d'etre for these companies is to sell their products and to increase their sales, to put it rather simplistically. And given that their products, being ultra-processed foods and beverages, have been demonstrated to be associated with incidences of various non-communicable diseases and increases of these diseases, there is no doubt that we have to decrease and reduce the consumption of these products to safeguard and improve population health.
Thanks so much, Edwin, for explaining your research and why it's so important to us.
Thank you so much for having me on.
Edwin Kwong there from the University of Melbourne in Australia. We'll put a link to the story that he and his colleagues wrote about their research for the conversation in the show notes.
And to end this week's episode, we've got some recommended reading from Lutfi Zulfikar, Youth and Education Editor for The Conversation in Jakarta, Indonesia.
Hi, my name is Lutfi Zulfikar, an editor at The Conversation based in Jakarta. After being dormant for around a year, Mount Sumeru, the tallest mountain on the island of Java, erupted again just a few days ago. The eruptions spewed out thick columns of ash into the sky, so far killing more than 20 people, causing many more to evacuate, and also caused a number of important bridges and roads in the surrounding area to collapse. Dian Fiantis from Universitas Andalas and also Budiman Minasni from the University of Sydney recently wrote an article detailing the history of Sumeru's eruptions since the early 19th century and how millions of tons of its volcanic material has affected the surrounding land. Our second story comes from Jaya Adin Linando, a management researcher at Universitas Islam Indonesia. A while ago, we published his English article on how religion influences Indonesian workers in seeking work-life balance. Jaya talked to more than 1,000 Indonesians from a diverse range of religious backgrounds and mapped out how their differing religious values affected the balance between their work and family. The research shows that religion has been very effective in becoming a sort of break or barrier against overwork amongst Indonesians. However, it also found differences in these effects, particularly between generations, with Generation Z being the least receptive of religion's influence in the workplace. That's it from me. Have a great day.
Lutfi Zulfikar there in Jakarta. That's it for this week. Thanks to all the academics who've spoken to us for this episode, and thanks to the conversation editors Miriam Frankel, Carolyn Salvi and Stephen Kahn, and to Alice Mason for our social media promotion.
You can find us on Twitter at TC_audio, Instagram at theconversation.com, or email us at podcast@theconversation.com, and sign up for our free daily email. Just click the link in the show notes.
If you're enjoying The Conversation Weekly, please leave a rating or review wherever podcast apps allow you to.
And tell your friends and family about the show too.
The Conversation Weekly is co-produced by Mend Marawani and me, Gemma Ware, with sound design by Eloise Stevens. Our theme music is by Nita Saul.
I'm Dan Marino. Thank you so much for listening.